Welcome, everybody. Thanks for joining Build a Modern Data Exchange Platform Analytics Workshop. My name is Ali Alemi. I'm a Senior Streaming Solutions Architect at AWS. And today I want to talk about some of the challenges that the large enterprises have when they want to exchange data across multiple line of businesses. Enterprises with multiple line of businesses often run into the challenge how they should exchange the data between their data silos and the data lake or across different line of businesses. This workshop has two sections. First, we're going to go through a few slides to understand the challenges and the solutions for them. Second, I have prepared a demo so you can see the solution in works. Before we get to that, let's quickly go over our agenda today. So we are going to dive deep into the large enterprises with multiple LOBs challenges. And then also we want to dive deep into the modern data architecture on AWS. Then we want to understand how modern data architecture on AWS is the answer to solve those challenges. Then we want to understand where to use batch processing and why a stream processing solves the challenges that we face in this particular use case. Then we talk about the transactional data lakes and why we would need transactional data lakes for building such an architecture. At the end, we recap by going over the solution and we have a few call to actions. As I mentioned, large enterprises with multiple line of businesses, when they need to exchange data, they often rely on traditional replication tools. Traditional replication tools do the point-to-point data replication and often come with some challenges. Because for every data source and data target, you need to define multiple endpoints. As the size of the systems and the number of the systems grow, the number of the endpoints that you define grows out of control. And that's why sometimes when the enterprise grows, these data pipelines become difficult to maintain. Also, they lose the flexibility, and then they need a central team to be centrally managed. As a result of these solutions are often expensive to scale and impose some security risk as a result of as a result of these endpoints need to be managed individually. So next, we want to talk about how we can solve these challenges. As you can see, the root cause of all these problems is the point-to-point data replication. How about we change our approach? At AWS, we recommend customers to use modern data architecture for building and modernizing their data architecture on the cloud. I'm going to go through some of the main and important pillars of modern data architecture. First pillar suggests a scalable data lake. A scalable data lake is a cost-effective, highly available, and durable data storage for storing all data with any size. Second is fine-grained access control, and third is unified governance. These features allow us to treat the data as a product. When we treat data as a product, we can decentralize the end-to-end data management and data pipeline. We decouple the data producers from the data consumers, and we allow each team to only perform their responsibilities. When there is an issue with the data producers are the expert in the data, and they are the only one know how to fix the data issues. Data consumers can only focus on consuming the data that they need and ingest that data from the data lake into their systems. We believe this model democratizes data production and data consumption so then each team is enabled to use the technology that is right for their use case among the broad portfolio of the services that AWS provides for building data pipelines. Modern data architecture on AWS recommends using the right tool for the right job. AWS provides a broad variety of the services based on the frameworks and open sources that they're right for each use case. We are going to dive deeper into the portfolio of the services a little bit later. And also I explain how did I choose the services in the solution that I'm presenting based on the use case that we are trying to build. In order to dive deeper into that, let's compare batch processing versus stream processing. Let's assume we want to sync the data between two data sources, from the source to the destination. The way the batch job operates, it takes a snapshot of the source database and it stores that on Amazon S3. Then the destination will need to run another batch job to import that snapshot into the destination. This will work, but then as you can expect, the latency of the data sync is unknown because this relies on how frequently the batch job runs. The batch job could run at some frequency, but we cannot run the batch job every hour or every minute. The reason is each batch job takes a little bit of a time until finish, and that time is in one-to-one relation with the size of the data in the snapshot. As the size of the data grows, the longer the batch job takes until finish. So then we need to set the batch job frequency such that we make sure that it finishes the work and we don't have multiple batch jobs running the same job at the same time. This introduces a big challenge because then the latency from the end to end can grow when the size of the data grows. In order to fix that, we need to change our approach. Stream processing works differently. When a streaming job runs for the first time, it takes the snapshot of the source database and then writes the snapshot on Amazon S3. From that point forward, the streaming job continues capturing the data changes and then storing them separately as delta files on Amazon S3. This way, the consumer would be able to read the snapshot first and then continuously ingesting the new delta files. And if all the events processed in the right order, the destination database can sync up with the source database very quickly, usually less than 1 minute. So this is a key idea behind the solution that we are going to propose in order to solve our first challenge, how we can build a low latency data sync across multiple systems using something such as Amazon S3 as a scalable data lake. Now it's time to understand where and how we should run a streaming job that qualifies all our requirements. Before that, I want to introduce you to several services that AWS provides as part of the AWS Data Analytics portfolio. These services are purposely built for data streaming. Data streaming mainly has three phases. In first phase, streaming ingestion requires a service that ingests the data from multiple sources. For that, customers can use Amazon Kinesis Data Analytics or Amazon Kinesis Data Analytics for Apache Flink, Amazon MSK Connect, or AWS Database Migration Service or AWS DMS. These services help you to collect data from multiple sources and ingest them into a streaming storage. The second phase is storing the data events in a streaming source. Streaming storage services include Amazon Managed Streaming for Apache Kafka, or a self-managed Apache Kafka on Amazon EC2, and then Amazon Kinesis data streams. For stream processing, customers can use Amazon Kinesis Data Firehose, or Amazon EMR, or Amazon Kinesis Data Analytics for Apache Flink, or Amazon MSK Connect. As you can see, there are a lot of purpose-built services, And we need to dive deep and understand a little bit which one of these services we should choose to build our solution. Let's work backward from the requirements that we mentioned earlier. We need a reliable stream processing framework that helps us processing the change data capture events. Let's understand what is a change data capture. Databases produce a log of the data changes as the transactions are performed on a database. A change data capture event is an object that includes the latest version of each record in a database. It also has more information. It has information about the value that the record used to be before the update or insert or delete occur. If it is an insert, the previous value would be null. If it is a delete, the previous value has the latest version of the record before it gets deleted, and then the current value will be null. And if it is an update, the before value will be the record before the change, and then the current value will be the record after the change. Also, it has information about the operation that took place, whether it was a delete, whether it was an insert, and then what was the timestamp that this occurred. So as you can see, the change data capture object has a lot of information, and it's much easier if we work with a framework that understands this format and provides a native service for these type of events. Let's talk about alternatives here. If we use a framework that doesn't understand change data capture, then we need to write branches in our code to tell computer what to do if it was a delete, what to do if it was an update, what to do if it was an insert. As you can see, you can do that for every single table, and you have to write that code over and over again for every single table that you are replicating from your source database. Apache Flink is an open source framework that provides support for CDC format, and that's one of the frameworks that we are using in our solution. Another challenge, as I mentioned, is we need some type of a data management in our data lake so we can distinguish the snapshot of the data from the change data captures that is stored in a small delta files. As you can guess, the streaming job writes many delta files, and those are very small files. We need a framework that compacts these small files into the larger files so then the performance of the reader does not suffer. To solve that challenge, we are going to use transactional data lake frameworks. So the rest of the presentation, we are going to dive deeper into Apache Flink and transactional data lakes, and then how we can integrate them in one solution. Apache Flink for stream processing allows us to work with a structure that is called dynamic tables. Dynamic tables are very similar to the tables that you are familiar in relational databases, but they continuously update. This is a very important concept in our solution because, as I mentioned, we want to work with a framework that understands the CDC and provides the data types that can support us in building such a solution. Apache Flink also supports a stateful computation, so when we need to join and aggregate the results, it can remember the previous result, and when it receives an update, it can update the previous result. It makes it much easier for us to do runtime analytics and aggregations to feed the downstream systems. It performs operation at in-memory speed, which is exactly what we need because we need a scalable and highly performant framework to work with the change data capture events. It does support the Debezium JSON format, which is one of the formats that you can produce CDC data. So next I'm going to talk about the transactional data lakes frameworks that can help us in our solution. As I mentioned, we need a framework that that helps us with managing files on our data lake. We have a lot of small files, and we need frameworks that can compact these to the large files, and also they can understand the deletes and inserts and updates. We need to implement the concepts of updates and deletes on our data lake so that a reader can always see the latest snapshot of the data and also can do things such as time travel. A reader should be able to read the same way as it would read from a streaming source from our data lake. So we need something that provides us that ability to go back in time and then read all the data changes from any given point in time forward. These transactional data lake frameworks help us. I have mentioned a few major ones here: Apache Hudi, Apache Iceberg, Delta Lake. All these frameworks provide support and connector for Apache Flink. You can use Apache Flink in combination with each of these frameworks to either write to a data lake or read from a data lake. If you read from a data lake, you would be able to set a pointer to read from a specific point in time until the latest and constantly reading as the writer job writes new files. This will help you to build a real-time job that constantly reading the data changes from a data lake and then writing it to your downstream database. Now let's take a look at the solution. So as you can guess, there are three different teams managing this solution. First is the data producer team, which needs to only build the pipeline for capturing their data changes and providing that as a product in Amazon S3 Data Lake. They have combination of different sources, and they want an ingestion pipeline that can capture the CDC data from all different sources and then be able to process that and send that and store that to Amazon S3. For ingesting the data, they're using Amazon MSK Connect, and they're using an open source DBZM connector on Amazon MSK Connect to capture the data changes and storing them into Amazon MSK. Same team uses Amazon Kinesis data streams for capturing the IoT device events and then storing it in Kinesis data stream. Apache Flink, running on Amazon Kinesis Data Analytics, can ingest the data events from the Amazon MSK and Amazon Kinesis data stream at the same time and join them together. This was necessary because the producer is the only team that knows how to enrich the data that receives from the IoT devices with the data changes that are coming from multiple sources, that are coming from multiple data sources, and then process them and send them to Amazon S3 Data Lake. In this solution, they are using Apache Hudi as a format of the transactional data lake to store those data changes on the data lake. Since the Hudi format is used for storing the data on data lake, the consumer should use Apache Hudi for consuming this data. In this case, consumer had multiple choices, but they chose a stream processing because they needed a low latency to pick up the new changes and send that into their downstream data store, which in this case is S3 Data Lake. They also use Apache Flink as it's a reliable framework for data streaming, and they consume the data changes in Apache Hudi format and store them in their downstream system. A central governance team controls the access between the producers and consumers. They need to make sure that the right people have the right access to the data. If there are other data sets in the data lake which this particular data consumer shouldn't have access, that's the job of the central governance team to enforce that access control. They have fine-grained access control through the tools such as AWS Lake Formation or the S3 or the S3 resource policies. Okay, We are going to switch to the demo and show you how this works in actual environment. I'm in the producer account now, and I want to begin with the data source. The data source is Amazon Aurora MySQL. In this MySQL instance, I have a database that consists of multiple tables. Here are the important ones: the customer, the site information, and the orders. Also, I have a Kinesis data analytics application which runs Apache Flink. You can have two types of Amazon Kinesis data analytics applications. You can have an application that is written in Java or Scala or Python, and then you package it and then you upload it and run it. Or you can have Amazon Kinesis Data Analytics Studio Notebook. A notebook provides you a development interactive environment, and this is what I'm using today because that's easier to understand and interactively explore the data. I have in my application, I have provided some dependencies as a custom Java archive library or jar files. So then they help me to write in Hoodie format and read in Hoodie format. Also, I have created this application in the same Amazon VPC as my source database because this application should be able to privately access the database and then connect with it so it can read the data changes. These are the list of libraries that I have provided in order for Apache Hoodie to work with Apache Flink. I will provide the list of these files later so then you can also download them to build it in your environment. So let's take a look at what the application looks like. All right. This is the notebook powered by Apache Zipline and managed by Amazon Kinesis Data Analytics, and I'm using this as my data producer. So before we begin, we need to set our checkpointing configuration so Apache Flink knows how frequently it should basically store the checkpointing. And checkpointing basically is a recovery feature of Apache Flink. Should anything fail, it will resume from the last successful checkpoint. Checkpoints include information about the environment variables of each operator. Next, I'm setting up some boilerplate. For example, the host name for my database and then the S3 URL that I'm going to write the result of the job. Next is where I define the structure of my source data. So as I mentioned, my data resides in a SQL database, and I need to tell Apache Flink what's the structure of those tables. As you can see, there are some metadata that are coming from the database itself. And this metadata is produced by the connector that I'm using to capture the data changes, or CDC. As I mentioned, CDC data has a lot of information with it. For example, the database name, what was the original table name, what was the operation timestamp. I'm interested in that data. And Apache Flink can parse that data and understands that data. It provides a native service for it. That's why I'm using a mapping to be able to ingest that data into pipeline as well. And these three are the original columns in the source table. I'm using a MySQL CDC connector, which I provided the Java archive library in my custom libraries part of the application. And I will provide the reference link for that. So you can basically ingest the CDC data the way that I use today without the use of Amazon MSK Connect. If you remember from this slide, I'm using Apache Flink itself to ingest the CDC data without the help of Apache Kafka. The rest are the configuration that is needed for connecting successfully to the data source. I repeat the same step for other tables, for example, the customer side and sales order table. As you may notice, this is very similar to familiar SQL structure that you used to work. And this is one of the benefits of Apache Flink because you can work with the streaming data using the SQL syntax, which makes it very easy. So in order for me to test everything is working, I have a simple select query that selects the data from one of these tables. Ideally, what should I see is a table that shows the latest snapshot of the data, and then if I update a record, I will see that record changes here in real time. So you can use this as an experiment in your environment, and you can run this query and update some records and see what the result would be. Next, I need to define some tables that also point to the product that I'm building on S3 Data Lake. So I created three tables, one for customer, one for customer site, and one for sales order. And I appended underscore hoodie at the end to distinguish the name from those from the source. These tables have information about what original table they're coming from, what's the record time, what's the event time, and then the other columns that match what we had in the source. I also want the data on S3 to be partitioned based on the customer ID. Partitioning is important when readers want to read the data to be able to filter the number of the files that they need to scan. The rest are Apache Hoodie configuration, and if you need more information on what these options and configurations are, I will provide a reference for you to read more about those. The main important thing here is that we need to provide a path where this Apache Hoodie data source is going to be located and where our streaming job writes its data. Another important option here is we define the table type as merge on read. Merge on read means that the writer can write with a low latency and then the compaction will occur later in an asynchronous mode, and it will compact the small files into the larger files later. Same configuration exists for other tables, except that the URL has a different location at the end that writes them in a different location in the same S3 prefix. So now that the job knows where to get the data and where to write the data, it's time to write the job itself. I have left a few insert SQL statements here for you. If you want to explore and if you want to run it, you can do it. And you can go through the same steps in your own environment. But for the sake of demo today, I'm going to run one of these insert selected statements only, which is reading the order data from the MySQL database and then writing them on Amazon S3 in Hoodie format. When it does that, it also does a very small transformation, which concatenates the database name and table name and adding a dot in between, and basically storing that as the original table name in our Hoodie format. Okay, so let's take a look at what happens when we submit this job. When you run this SQL statement, this notebook interprets this as a streaming job and it submits that streaming job to Apache Flink cluster. When I go to Apache Flink dashboard using the provided link on the notebook, this is what I usually see. Each of these blue boxes representing a task in the streaming job. I will zoom out so you can see all those blue boxes, and I explain a few of them just so you know what is happening here. So one task is responsible for capturing the change data event. Another task is responsible for determining how these events should be aggregated with each other and then constitutes a single file. The stream writer consists of multiple tasks which run in parallel to write these files on Amazon S3. And at the end, these are the compaction tasks that they run with a certain frequency to compact the small files into large files. So you can see a lot of these complex tasks have been just compiled and submitted by Apache Flink SQL API. So with a simple SQL query, I was able to build a relatively complex job, which is helping us in building and maintaining data replication pipelines in a very easy way and maintainable way. Let's verify if this is working. So here's the location that I'm writing the hoodie data set for all the sales order. As I mentioned, I have some element of partitioning, and in case of sales order, I'm partitioning based on the shipment mode. Each shipment mode is indicated here, and if I click on it, I will see all the files with that prefix on Amazon S3. As you can see, I have a combination of Parquet files at the end and some log files over the top. This is because the streaming job will write quickly the Avro files in the raw format, and then Apache Hudi compaction will compact these files later into larger Parquet files. So each of these Parquet files basically has the latest snapshot of the data, and then the reader can quickly, in a read optimized manner, read all the records, and then the streaming job at the same time can just write the Delta files and move on. This separation brings many performance benefits, as you can imagine. The data governance team should provide access to this location on Amazon S3 to the consumer with the read access, and also should provide access to the data catalog objects that Apache Flink created as a result of those defined table statements. Let's go back and visit them again. Each of these tables are created within AWS Glue Data Catalog. This is because AWS Data Catalog is a Hive Metastore compatible service for Amazon Kinesis Data Analytics. And when Amazon Kinesis Data Analytics wants to store anything in a Hive Metastore or Hive compatible Metastore, it will use AWS Glue Data Catalog. And these objects are now created in there. These objects could be shared with the consumer, or consumer should create another one in their own account. So both are possible, and then you can choose which is the right one based on your use case and security model. In this solution, we are sharing them using AWS Lake Formation with the data consumer, so then the data consumer does not have to create these tables over again. Once that is shared with the data consumer uses a completely different notebook. This notebook runs on another Kinesis Data Analytics application, which basically is having the same configuration as far as the custom connectors go. These custom connectors, again, will be needed because we need to read files in Apache Hudi format, and we need to provide these Java archive files or jar files in order to be able to use Hudi connector. Again, we set up our checkpointing, which we set it for 30 seconds. And then since the table is shared with us, we don't have to create it again on the consumer side, and we can just directly select from it. This consumer wants to run some real-time analytics. So they want to count all the orders and they want to just have a live dashboard that shows the count of the orders, total count of the orders per each shipping mode. They also have a column that shows the latest update time of these orders. So they can track it, for example, what was the last order took place. So now in order to test the pipeline end to end, we are going to use a notebook that inserts a record into our source database. And then we are going to observe this count to make sure that we see a live update in here. And then we also observe the latency. Okay. For that, I have a notebook prepared here. This notebook is pure Python. It just uses my SQL client in order to connect to the database and run an insert query to insert a new order. So let me run that again. So a new order with this ID is now inserted. So we go back to our consumer and we are going to watch our count, and we should see an increment in the standard shipping mode because that's the record that we inserted. The new count should show number 14,769. We are expecting about less than a minute latency because we set our checkpointing at the writer and the reader the 30-second. So then the latency should be under a minute. As you can see, less than a minute, we got a new count of the standard shipment with the latest updated time, which matches the time that we are right now. And this is the UTC time that's I'm showing on my screen. So as you can see, we've been able to decouple our consumers from the producers by providing a scalable data lake in between. So then the consumer can use the technology of their choice, and then the producer can use their technology of choice, and they can work without having dependency on each other. Now let's finally check our Amazon S3 files. Let's see if there is a new file is written in here. So we have the count of 25 files until now. So if I refresh, now we see 27 files. The reason is we got a new log file, and then Apache Flink job quickly compacted the latest result into another Parquet file, and that also has been added here. If you're interested in learning more about these concepts that I mentioned in this demo, please go to these links as each of them help you with a specific topic. If you want to learn more about the modern data architecture on AWS, the first link will be providing a lot of deep knowledge about the modern data architecture. If you want to learn more about the Apache Flink framework and its use cases, please go to the Apache Flink official documentation. If you are interested in using Apache Hudi and want to download those jar files and use it in your own environment, go to the Apache Hudi official Flink guide. I wrote a blog about a year ago that provides you a CloudFormation template. So you can get this environment up and ready very quickly using that CloudFormation template, and also provided some instructions for running the same job on Amazon EMR. And if you're interested in getting that environment and the stack set up quickly, you can use that blog, which is labeled with create a low latency source to data lake pipeline. If you're interested in learning more about Kinesis Data Analytics service that provides a serverless infrastructure for Apache Flink, please go to the official documentation. And there are more resources for introducing Kinesis Data Analytics Studio and also Kinesis Data Analytics for Apache Flink. Thank you for watching, and thank you for trying this solution in your own environment. I hope you enjoyed and learned something today. Please provide your feedback, and please provide your comments under the video so we can improve these videos for the future. Thank you very much.